Continuous random variables. Sometimes you will see me writing continuous random variables as CRV. Yeah. Okay. CRV. There you go. Okay. First, when you have a continuous random variable, let's say X, right? When you have a continuous random variable, it can only take a range of values. Yeah. That's by way of definition, right? What is a continuous random variable? A continuous random variable is a random variable that can only take a range of values. What do you mean by a range of values? What I've written here, right? X bigger than 4, X less than or equal to 4, X between 3 and 4 inclusive, X between 6 and 7 not inclusive. So this is what I mean by can take a range of values. Okay, so it will never be X equals to 4. Okay, you will never have a situation where you're asked to find the probability, okay, that X equals to 4 if X is a continuous random variable. Okay, it'll never be. You'll know in a minute why, because of the fact that, when we talk about probabilities for continuous random variables, we talk about areas below graphs. Yeah. So quickly, the important thing that I've said so far, when you have a continuous random variable, it can only take a range of values. Okay, good. Also, before I leave this, these things, if you ask to find the probability that X is bigger than or equals to 4 and X is bigger than 4, the answers will be the same. Yeah. Okay. If I ask you to find the probability that X is at least 4, probability that X is bigger than 4, these answers that you work out will be the same. And so you don't have to worry about the equal to symbol here. Okay. Whereas for discrete random variables, the answers will be different, right? Okay, good. Probability distributions, right, for continuous random variables are given by mathematical functions. Now, and they're known as probability density functions, okay, PDF. Let me say that very important point again, right? Probability distributions for continuous random variables are given by mathematical functions, and they are called probability density functions. Yeah, and this is your notation, right? This one here, f, small f, right? Or small case f, and this one is the random variable that we are talking about. Okay, and so if you're asked to find a probability, right? So I've written it here again, right? The probability x between a and b inclusive is the same as the probability of x between a and b not inclusive, and it's given by an integral, right? Let me clear this. Yeah, it's given by an integral. Okay, you integrate f of x dx with this, excuse me, you integrate fx with respect to x, taking the limits going from a to b. And from our calculus days, we know that this is the area below the graph, right? So if you have f of x this way, then we have got a and b here. So this will be the area of the graph. Okay, good. Now that we have dealt with PDF, right, probability density function, let's talk about the CDF, yeah, the cumulative distribution function. So definition is the same, right? This tells you about the random variable that we're dealing with, and this is equals to the probability x less than or equals to x. This is the same, right? The definition is the same as what we've seen before. So what we do now, we have to set this form, okay? We have to write this in the form of an integral. So less than or equal to x, so your upper limit is x, and we take the lowest value of x that's possible. So to make life easy, we just write negative infinity to x, f of t dt. Okay, the reason we write f of t dt is because we have x in here, so it doesn't make sense to write fx dx, right? So you write it as f of t dt. Okay, also take note, we have said this before, when you differentiate your CDF, you'll get your PDF. Okay, differentiate CDF, you'll get your PDF. Let's look at a couple of examples, and then things will begin to look very smooth. Yeah. Okay. We have a very simple example. Let's work from the easiest case and then move on, yeah? Okay. We are given the density function. The PDF is 3x squared, x squared from 0 to 1, yeah? So if you draw a picture, it'll be something like this, okay? So this will be your 3x squared, your curve, and you're going from 0 to 1, yeah? You're told that this PDF is valid for values of x between 0 and 1. So if you are asked to, right, let's say find probabilities, find CDFs, and so on, we are going to use this, yeah? So let's start slowly. What happens if you integrate from 0 to 1? We are told that this density function is valid for values of x between 0 and 1, right? So what happens if we integrate from 0 to 1? So I've done that here for you, 0 to 1, 3x squared dx. Okay, let me say that again. We are integrating the density function. We are integrating the density function from 0 to 1. And when you do that, you will get, x cubed, right? When you integrate this, you will get x cubed. Okay, and the limits are 1 up there and 0 here. So you'll get 1. So you know straight away that this is a valid probability density function because total probability must be 1. Okay, total probability must be 1. Okay, that having been said, let's look at your CDF. The CDF is quite easy. Yeah, just make sure that your upper limit is x, right? And your lower limit, don't write negative infinity, right? Your lower limit will be what? 0, right? Because that's the smallest value x can take. So you go from 0 to x. Remember I said you use t, right? Use f of t. So 3t squared dt. Clean this up a little bit and you'll get your CDF as x cubed for values of x between 0 and 1. So if you're asked to find the probability that x lies between 0.2 and 0.6, okay, if you're asked to find that probability, you can go ahead and do the integration, okay? You can go ahead and do the integration of your probability density function using the limits 0.2 and 0.6. But hey, you already have your CDF, so why don't you write f of 0.6 minus f of 0.2, okay? Since you already have your CDF, just plug in and you'll get your answer, okay? Good. Now that we have cleared the basics out of the way, so let's go ahead and deal with first moments. Expectation, right? Let me move this up, yeah, so that we can see this clearly. Good. Okay. So we have the expected value of x. Let me write it here, right? The first moments is always the integral x fx dx. Okay. All you need to do is just take care of the limits. So here to cover the general case, let's write it as minus infinity to positive infinity. That's what you see here. And if it is the expected value of x squared, doesn't matter. Okay. Expected value of x squared will be what? Just replace this with a x squared. And that's it. Okay. So first moment, second moments, and then you know the variance, you know how it works. It's just your second moments minus your first moment squared. Nothing changes. Okay. So in our previous example, right, we had our density function 3x squared, right? That was our density function. So if we asked to find the expected value, just write it as x fx, right? X fx. And then we integrate. Don't forget the dx. Okay, this times this. And what are the limits? 0 to 1. That's what you see here. So when you do the integration, right, this is very easy to integrate with 3x cubed. Okay, we have 3x cubed. So write down 3x to the power 4 over 4, and you'll see this appearing. Yeah, can you see? And then plug in 1 and 0, you'll get your answer. The expected value of x is 3 over 4. Okay. Similarly, you can find the second moments, expected value of x squared, except this now becomes x squared, 3x squared dx, going from 0 to 1. And you plug in all the numbers you plug in all the numbers, you'll get, not that difficult to do, right? It's 1 and 0 anyway. So it's just 1 times 3 over 5, you'll get 3 over 5. Variance of x, second moments, this is the notation, right? Sigma squared, that's the variance. And I have 305 minus 304 whole thing squared, you'll get your answers. If you're asked to find standard deviation, just take the square root. You can also write, you can also work out your variance, right? Using the, what do you call it? The definition of variance, right? Okay. Remember, we talked about this last time. Variance is your second central moment, right? Your second central moment. So it's the expected value of x minus mu whole thing squared. So you can also work it like this, okay? X minus mu will be x minus mu, what's mu? 304 squared, and then your f of x, right? Remember, the expected value of g of x, okay, would be what? Minus infinity to infinity, g of x, f of x, dx. That's what we're using here, okay? That's what we're using here. Don't forget there's a squared here, and this is your PDF. Go and clean it up, and you'll get 3/80, okay? I've written the expected value of gx here, okay? Just as a quick review. And some formulas that come to mind, the expected value of ax plus b will be what? The linearity principle, right? It'll be a times the expected value of x plus b. Expected value of x plus y will be expected value of x plus expected value of y. We've seen this before. And if x and y are independent, okay, if x and y are independent, then the expected value of x times y will be expected value of x times the expected value of y.